Hey guys, how you doing? Welcome again to my office. Okay, so as advertised, I have to be downtown Wednesday morning, so I cannot give my lecture live like I normally would do. I'll try to make sure this happens as little as possible. In fact, hopefully this could be the only time this term. Um, but certainly it has to be true for Wednesday. So I'm just going to continue the lecture here and make sure we get all Chapter 4 taken care of course, because you have an M-tuner at the end of this week. All right, so let me just jump in. Third lecture on Chapter 4. Just to kind of put this in context a little bit, we've been talking in the first lecture in Chapter 4 about the visual system and really focusing on, the raw sensory input and some of the ways it's processed by the eye. Then in the second lecture, I talked to you a lot more about how the brain makes sense of what's coming in and the role that memory plays and our biases play in terms of how we see things. And I also made a point at the end to show you that our brain has trouble seeing things in multiple different ways at once. It tends to see things in a certain way. And so even these ambiguous figures that people can see, the younger or the older woman, or the Necker cube one way or the other, still our brain can only see one of those at a given time. And so I tried to give you a sense of how that's about. So the ultimate goal, by the way, of a lot of that Gestalt stuff and such is to help us organize this chaotic input that's coming in. Ultimately, we want to organize it to get at some issues that I'm going to highlight here. What are the things in my environment? Where are those things? These are things we have to know to function well in the environment. I'm going to add a little bit of who there as well. So recognizing objects, but also recognizing ourselves or others. I'm going to bring a little bit of that in because humans are very important to us, and they're special. Faces and people are very special stimuli. And so I want to talk a little bit about how the brain kind of is especially focused on those. All right, so let's go in. Again, when we have all this input, let's stick mostly to vision here now, but all this input is coming in, and the ultimate goal of our system is, well, I said to make sense of it. And part of making sense means recognizing what those things are. So the light bounces off objects in our world and comes to our eyes. And our eyes now want to figure out what those objects are. That's at least one of the important things. So if you look at these, for example, I could say, well, where are the dogs, for example? And you could see, okay, there's a dog, there's a dog. Is that a dog? Well, no, that's not a dog. It kind of looks like a dog, but it's not a dog, it's a horse. So you've learned subtle distinctions between things. Now, the interesting thing is some of these things you've probably never seen in exactly this. Like maybe you've never seen this truck from that angle, and yet you still know it's a truck. In fact, you can probably tell it's a toy truck. I don't even know why, but we can tell it's a toy truck here. So even things we've never seen before, from the specific angle we're looking at it, we can recognize that these are headphones. And our system is very good at figuring out what things are. How does it do that? Well, we seem to think there's sort of two things at play, maybe one more than the other, but let me do it historically. When people started worrying about this issue and thinking about it, they really focused on things called defining features. So, for example, a chair. What is a chair? Well, let's go to Wikipedia. What's Wikipedia say? Well, one of the basic pieces of furniture, a chair is a type of seat. Its primary features are two pieces of durable material attached as back and seat to one another at a 90-degree or slightly different angle, with usually the four corners of the horizontal seat attached in turn to four legs, or other parts of the seat's underside attached to three legs, or to a shaft about which a four-arm turnstile on rollers can turn, etc. You're already seeing that they're having trouble with the legs, because chairs have all these different kinds of legs. But even if you think of this, back in a seat, so here's the two primary features, are two pieces of durable material, the back and the seat. Okay, when people started thinking about how the brain recognizes things, they thought it was looking for specific so-called defining features, certain things that tell us, oh, that is a seat. And if we took this description, you know, these would probably be the most primary, a back and a seat at about 90-degree angle. That defines a chair. Here's the problem. If you come to my office in my office hours, in fact, I can show you. Some of the chairs look like this. What the heck? Just like the one you see there. Well, does it have a back and a seat at one another 90 degrees? No, this doesn't. It doesn't even really have an obvious seat. I mean, obviously you can sit on this apparently, and you can. It bounces, by the way. It's fun. But at any rate, this would be fail to be recognized as a chair. Now, truth be told, when people come into my office and they see these, they do a bit of a double take, like, whoa, is that supposed to be a chair? But it doesn't take them long to sit on it and recognize it as a chair, and react to it in that sort of way. So this has been a problem with defining features. Anytime we kind of think of something in the environment and try to figure out, you know, what are the features that make that thing what it is? We can almost always find exceptions. And so how does the brain deal with the exceptions if it's using defining features to recognize things? People have come to believe that yes, defining features help. That when the brain can lock on to some feature, that might make it easier to recognize something. But most psychologists don't think that is the primary process of recognition. They think of it a little differently in terms of something called like fuzzy matches. What is this thing? Most of us would probably say it's a six-legged dog, but we still think it's a dog. We still recognize it as a dog. Even though in this case, probably the defining feature of most dogs is 4 legs. And so 6 legs is like some dogapede or something. It's something really weird. How do we recognize that? Well, if I break out of here for a second, I copy this image. I think I can. Oh, can I not copy the image? Son of a gun. So I'm going to find it again. So I'm going to go to Google. You'll see this image later. And I intentionally put that in there. He's here somewhere, trust me. I found him. There he is. So I am now going to copy that image. So imagine now we see this out in the world. I don't know if you know you can do this, but on Google you can search by an image. So we can actually use the image instead of words as our search cue. And we can say, show me similar images. And here we have some similar images. How the heck did it do that? It literally kind of takes that image form and it compares it to everything it has in its database. And it looks for things that kind of match, that kind of look similar somehow. And these are some of the things. And you notice in some cases it's really locked onto the legs, right? But in other cases it's probably more the face that looks similar. This one, I guess it's the face, etc. But if you kind of look at the things it brings back, okay, look, we got some monkeys here. We got a really poor dog I don't even want to look at, little guy. I don't know, 8-legged cat. We got an 8-legged cat. It didn't just return dogs. Here's some poor little deformed cow. Here's a dog sitting on another dog, etc. It's returned a variety of things, but when we look at them overall, most of these, the vast majority of these things are dogs. And so you can imagine a search that starts by following, what have I experienced in the past that's similar looking to that thing? And then if I retrieve a bunch of things that are similar looking to that thing, is there anything that most of those have in common? And in this case, even though there's huge differences between, say, this picture and this picture, they are both dogs. And so through most of these things, what they have in common is that they are dogs. And so when we see this image, we see it as a dog. Now, we may see it as a weird six-legged dog, so we may recognize early on, like, okay, it looks like a dog, but something's not right. And maybe defining features play a role here. But the idea is this is more the way the brain does it, that we actually use the image coming in to query our brain, and then our brain, in fact, as it starts to find similar things in our memory, affects how we perceive this. That's what we talked about a lot in the past lecture, right? How memory was actually affecting how we saw certain things. But it also helps us to recognize what that thing is. And so it's what's sometimes called a fuzzy match, because it's like we never find an exact match to this thing, and we don't have to. We can just find things that sort of match, that match in a sort of fuzzy way, and then we can look at what they have in common and derive information from them. So we think this is mostly how the brain recognizes what things are, and this is why it can recognize things it's never even seen before, as long as it's seen things that are similar to that thing. It can still recognize what it is. Let me kind of rip apart the word recognize for a second. Recognize. Recognize. Cog meaning think. So it's like thinking about something again or bringing back a thought. When we talk about recognizing something, we're talking about, you know, pulling something out of memory and rethinking about it again. And so we can even recognize things we've never thought about before or never seen before. But if we've seen something similar, then we can know what that thing is. I hope that made sense. I only have so much time to focus on some of these things, so I'm going to kind of jump to another question. Okay, it's one thing to look out in the world and kind of recognize the objects one sees. But if you want to interact with those objects, then you need to not just know what they are, you also need to know where they are. Are things close to you? Are they far away from you? You want to get a sense of your world that is a three-dimensional sense. So how do we do this? Well, having two eyes helps, although it's not necessary. I will show you an example from shading in a second, where I'll show you that it's not necessary. And in fact, one of the things I often, when I'm in class, and when I'm doing this in class, I like to do a demonstration, and the demonstration involves me asking somebody to come to the front of class, and you can do this with a friend of yours if you want, and we pick something that we can throw back and forth that isn't going to hurt anybody too bad. If it were me in that class, I'd probably pick that big blue dice microphone, and we stand far apart from each other, and I begin by saying, okay, let's have both of our eyes open, and let's throw this to each other back and forth. And what you tend to see there is a pretty smooth throwing back and forth of the object. If I'm the catcher, you will tend to see me adjust my hands while the object is in the air to be in a position to catch it and cushion it well. So you see a nice smooth ability to, especially if you look at the catching, to catch the object well. So try this with a friend. Throw something back and forth, keep both your eyes open, and just kind of pay attention to what your hands are doing and what your body is doing to catch that object. Now, let's just be clear about what your hands are doing. Your hands are doing something we call depth perception. They are figuring out where that object is, not only now, but where it will be when it gets to you, and they're inferring that and trying to be prepared for that. Okay? And with two eyes, we can do that very well. I'll explain to you why in just a moment. Then what you do is you each close one eye. So just continue to throw the object back and forth, but close one eye. You will notice two things happening. The first thing is you can still do it. It is not like depth perception requires two eyes. It does not. You can do depth perception with just one eye. But you will also notice that you don't do it very well anymore. You're not graceful. So with your two hands still will adjust while it's in the air, but you'll adjust in a much jerkier kind of way last minute, and you'll drop the object more often. So yes, you can do depth perception, but you can't do it as well. Something about having two eyes helps. Okay, what is that? There's two things, and I like to talk about these ones. There's a bunch of things you can do with one eye. I'll let you learn about those from the textbook because I don't find those as interesting. I like these two-eyed things. So I'm going to focus mostly on the two-eyed things, although I do like the shading thing, so I'll show you that too. But let's do the two-eyed things, so-called binocular cues to depth. Oh, okay, so I start with the monocular. Okay, let's start with the one eye. The one eye thing does make a really good point that I want to highlight, and it's the point that we've made in last class, but it allows me to make it again here. How important our memory and previous experience is to determining what we perceive. Let me start by freaking you out. Okay, and let me make this bigger while we're doing this. Okay, let me get rid of this, make it even a little bigger. Here we go. Pick one of these. Let's say this one. Now, what I'm going to do, I'm going to just click on this, and I'm going to just rotate this around 180 degrees. When I rotate it, this one will end up down here, right? I'll rotate it around and it'll end up down here. But what I want you to notice before I rotate it is when you look at these things, what do you see? Some of them are what are called concave, these 4, and some of them are what are called convex, these 6. So convex means it's like a bowl coming out at you, right? Whereas the concave, it's going away from you. It's like a cave entrance, walking into a cave, as it were. Whereas this one feels more like a sphere coming out towards you, okay? Watch what happens to this sphere as I spin it. Right now, it's coming out towards us. And in fact, if you look more globally, we have 6 coming out towards us. These 4 are going in. Spinning, 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 boom. What happened? Well, hang on. The ones that were sticking out are now going in. And the ones that were going in are now sticking out. Let's do that again. Oh, sorry, I got to spin down here. I'm going to do it quick first. Uh-oh. We're back to where we were. These ones are now sticking out. Middle ones are now sticking out. Middle ones are now going in. Middle ones are now sticking out. What the heck is going on there? Well, notice the dark and the light. Turns out it's very important. Imagine this was a cave. Where is the light source in our universe? Well, it tends to be up in the air. It tends to be high. And if light shines down on a cave mouth from above, well, the floor of the cave might be lit, but the roof is not because it's shaded, right? So this, when you have bright at the bottom and shade at the top, then our brain thinks, because it assumes a light source at top, our brain thinks that's going away from us. Compared to, say, this one. Now imagine this was a sphere coming out towards us. That's what it looks like. It looks like that because, again, we assume a light source from on high. And when the light comes down from on high onto a sphere, it lights the top of the sphere, but the bottom of it is in shadow. Okay? So this is how light works in the real world. In a cave, it lights the bottom but keeps the top dark. In a sphere, it lights the top but keeps the bottom dark. What your brain does is flip that on its head. That is, it determines what you see based on the light and dark because of its experience in the world with caves and spheres. It now assumes that anything that's lit on the top and dark on the bottom is coming out towards you, and vice versa. And so the same object, if you just reverse the light and dark, it suddenly looks like it's going the other way. Now, that theory should predict, and let's do this now, that if we did this slowly, more slowly, well, what happens? It's still kind of, well, what is it? What is it here? Is it concave or convex? So you can play with this yourself with their own PowerPoints, spin it around, and you can find that in intermediate positions, it's not as obvious what's concave and what's convex. It's a little bit of a mess, and it's really not till you get somewhere around, like even here, where the external light source might be up and to the left. But once you get a little bit more of a directionality in the light source, then you start to see these things popping out. Okay, so we're getting an illusion of depth based only on the light-dark, the shading. But again, the bigger point of that is that you can get this with one eye, by the way. You could do this whole thing with one eye closed. It won't be any different for me. This is just the shading that's causing this. So I like this as a cool example, first, of how memory is affecting what we perceive. Again, I think those examples are always very important. But I also like it, to show that, even if we only had one eye, there's all this kind of information available that gives us a sense of how far things are from us. However, if we have two eyes, it's even better. So now let's do two eyes. One of these things is kind of simple. The other, in my mind, is mind-blowing. So, convergence. How do we know how far something is away from us? Well, the very simple idea of convergence is the following. If we take some object and we vary how far it is away from us, you will note that, and I'll let you look in my eyes, look deeply in my eyes, as it's relatively far away, my eyes are, I don't know how to, you'll notice, when I bring this closer to me, if I try to pick a point, I'm going to pick a point on that thing and look at it, watch what happens to my eyes themselves. Okay? So eventually they start to look in, and you can actually go cross-eyed at some point if you want to, but you don't want to go cross-eyed. But the further it is away from me, the more my eyes do this. And when it comes closer, the more they do this. So it's convergence. And I just show you that down in the picture here. So something that's closer, your eyes are pointing and making a bigger angle, as it were. But as this thing goes further and further away, they're actually looking a little straighter, and there's a smaller angle of discrepancy between them. And so we have muscles on our eyes that can detect how bent or convergent our eyes are, how non-convergent or convergent they are. And that muscle sends information to our brain. And so that is one very important source of information. As we look out in the world and focus on an object, every time we focus on an object, we get clear information about how far that object is away from us. Okay? Not particularly shattering, perhaps. The next part, I think, is retinal disparity. It's a complicated kind of concept, but let me try. Whenever we're not focusing on an object, okay, let me say it this way. When we focus on an object, what that does is it puts that object on the exact same spot, or in fact, the mirrored spot, but let's call it the same spot, on each eye. Okay, and that allows us to see it very clearly in a lot of detail. But we're only seeing that, we're only having that happen for the thing we're looking right at. For everything else in the world, there is what's called retinal disparity. Where the image of that thing falls on one eye is different from where it falls on the other eye. And although we don't normally even notice this, what that actually produces is two images, or a double image, of everything we're not focusing on. We don't see it, but our brain can detect that, and it can use it to figure out where everything else is. Convergence tells us where the thing we're looking at is. Retinal disparity tells us where everything around it is. Okay, I know, that sounded like magic. You don't believe it till you see it. Here's the test to see it. Hold up two fingers. And I'm going to show it to you this way first. Hold up two fingers. Focus on the knuckle of your front finger. So that's where you're going to be looking. And you're going to keep your eye looking there. But as you do that, move the second finger away from you. You will see very clearly that there isn't a second finger. There are two second fingers. And the further you move that second finger away, the further apart those two other hands become. It's really freaky, man. It messes you up. It messes you up in part because you don't notice that this is happening all the time. with things. This demonstration kind of makes you aware of something you're normally not aware of. Why are these things moving apart like that? Well, the further they are from you, the more retinal disparity. So one eye sees the finger in one place, the other eye sees the finger in another place, and the further that is apart, the more discrepant those two places are. So what this says is when you're looking at some object in the world, again, convergence is telling you where that is, but everything around it, there's actually two versions of it. And the further those things are, the further this disparity is, and our brain senses all that too. And it uses that to figure out where all the distracting information is. And so when we're done, we know them both. We look at something, we know where it is, and we know where things are around it. That's freaking cool, isn't it? I think that's freaking cool. By the way, when you have two eyes, these phenomenon that we just talked about, convergence and disparity, are more extreme as your eyes are further apart. The further apart your eyes get, the more powerful these processes become, and therefore the better your depth perception, the better you are able to see and understand where things are in your world. This is why animals that tend to be prey, like rabbits and mice, etc., tend to have wide eyes, but not just the prey. Sometimes these predators also tend to have eyes that are a little wider. They can think of a hawk, a bird, that has the eyes a little bit more to the side of its head. That allows it to perceive depth well. So things that attack or have to defend at a distance, need that information well ahead of time, they tend to have eyes further apart. That gives them poorer acuity. They can't see things as sharply as you can when your eyes are close, but it gives them better depth perception. We are somewhere, we favor acuity, but again, our eyes are still separate because that separation gives us depth perception. Okay? Cool. We've talked a little bit about how we know what things are. We've talked a little bit about how we know where things are. I want to now just sort of finish this one by highlighting this special stimulus. Humans, I will make this point over and over and over again, we rely so much on our social relations, our social connections. They insulate us against fear and grief and all those sorts of things. They are our support network. It's very important that we respond well to the humans around us, our friends, our family especially, even our acquaintances. And one of the first steps, by the way, in forming a bond with another human being is to recognize that human being when you see them again. It's really embarrassing when you're at a party and you're talking to somebody and that somebody says, oh, by the way, we've chatted before, and you realize, oh, I didn't recognize them. And then you feel like an idiot. Like, oh, I should have recognized it. It's like I didn't care about my previous interaction or something. And so we could take offense, by the way, if we've met somebody 3 times and they still never recognize us. It's like, obviously they don't, I don't know, we haven't made an impression, so to speak. So facial recognition seems to be a very important part of social bond making. And it seems like the brain has in fact recognized the importance of this to the point where there's a part of the brain called the fusiform gyrus in so-called Brodmann's area 37. So I'm showing you it here. Now notice it's kind of between occipital and temporal, right? Sort of at that mix. It's on both sides, on both the left and the front, both the left and the right, the fusiform face area. So we have them both left and right sides of our brain, and it's kind of stuck back there, close to our occipital lobes, but not right in the primary action thing. But certainly when we get visual input coming in into the primary occipital area at first, this is one of the areas that input goes to. And if that input is part of a face, this is the part of the brain that recognizes who that face is. Now, an important thing about faces, to think about this, is that there is nothing distinctive about your eyes. There is nothing distinctive about your nose, or your mouth, or your ears. We could find other human beings that have eyes like yours, nose like yours, a mouth like yours. What we have trouble finding, unless you're an identical twin, is another human being who has those things in the same places. It's the way those things relate, where your ears sit relative to your nose and how far your eyes are apart and above your nose but close to your ears, and where your mouth is and how big, and etc. So it's all these different bits and how they all come together that matters. That's what the fusiform area seems to specialize in. Looking at these configurations of facial elements and then recognizing specific configurations as being associated with specific individuals. That is the face of Tom Cruise. That is the face of Morgan Freeman, etc. There's some weird things I like to tell you about these, just to kind of let you know. Some of the studies done on these have shown some weird conditions. There's one condition called prosopagnosia. That is when people have trouble recognizing a face. And an interesting thing is they can still feel the familiarity. So if you showed them these faces and you have these four versus these four, I'm suddenly worried about something. I'm not sure. That's weird. We'll come back to it in a second. Most people can say, oh yeah, these four on top are much more familiar. Okay, I've experienced these faces before. But if you say, who are they? People with prosopagnosia, which is damage to this area, they can't tell you who these people are. They can tell you they're more familiar than those people. And if you made them guess, they might say things like, well, maybe this is my brother. Or maybe my uncle or something. Or maybe it was a good friend from high school. Or maybe it was a movie star, which in this case would be right. This is Tom Cruise, by the way. But this individual, you know, where is this guy famous from? So in case you don't know, this is George Bush. This is John Travolta. Is this Heather Mirren? I don't know. I'm not exactly. I know the face. So now I'm just like a prosopagnosic with her. I know the face. I know it's familiar. I know she's from the movies, but I can't peg her exact name. So I can't actually recognize her. That's how a prosopagnosic would be for everybody. And in fact, if you included their brother or sister's faces in here, they would again say exactly the same thing. This person looks really familiar, but I don't know who they are. Okay, they've lost their ability to recognize faces. I'm suddenly freaking out because this is my face. I think I might have been, I might have contributed my face to this research study. I'm not sure, but this one looks familiar too, so I'm not sure. Anyway, there's the reverse of this, which is even more fascinating in a creepy way. Prosopagnosics detect familiarity, but they can't recognize the actual face. There's another syndrome called Capgras syndrome, which is the reverse. People can recognize a face, but they don't feel familiar. It's a different part of the brain. We won't get into that, but it's just a fascinating phenomenon. Well, it's fascinating partly because of what happens, which sometimes is not good. These people can do things like the following. They'll go to a doctor and they'll say, listen, there's this guy I'm living with, and the doctor will say, well, you mean your husband? And she'd say, well, you know what? He looks like my husband. He sounds like my husband. He acts like my husband, but he's not really my husband. And the doctor says, well, what do you mean? If he looks like him, sounds like him, acts like him, and they'll say, because there's something not right. There's something, well, he's not familiar. He's not. And so they're saying, I recognize all these features, and I know who that's supposed to be, but they don't feel right. So normally when we're recognizing somebody we know, there's what they look like, but there's also this other thing that makes us feel like we know who that person is. And the Capgras people lose that other thing, which we'll call familiarity, but it might be more than familiarity. But it just feels like that person's a stranger. That's how they feel, even though the person looks right. In the extreme cases of Capgras, in one case especially, somebody murdered their husband. They murdered their husband to show others that in fact it wasn't their husband, it was actually a robot or an alien disguised as their husband. They could think of no way of convincing, nobody would believe them, so they thought the only thing I can do is cut their head off. And if I cut their head off, that will expose the wires or the alien blood or whatever it is. And it turns out that, well, it was their husband. So they killed their husband. That's how strong that effect can be. Okay, so I just thought I'd throw that out there to kind of wake you up a little bit. There's also, and maybe this is easy to you, who is this person? Could you detect right away? Maybe you could detect right away. But there's a lot of evidence that suggests it's not just the configuration of the face that's important, but it's also the orientation of things. That when you present famous people, and she's probably too famous for me to use for you guys, but if you present famous people, but you present their faces upside down, like we could even try it with this one actually. Let me go back to here. Whoa, what the heck is going on there? Yeah, go away. This is my other slides. All right. So, you know, we could have even tried it with this. If we present these ones upside down, now look at these guys that were familiar at the top, and now they're getting much harder to recognize right off. But you put them upside right, you can recognize her. If any of you have had trouble recognizing her, well, let me put her upside right, and it's probably like, boom, easy. So this fusiform area is fussy about the orientation of things and being quite, you know, just right. It doesn't care, by the way, if you darken your eyes or put lipstick on or whatever. That doesn't mess with it too much. It's really about the core features of the face and how they are oriented with one another. Okay. So now I want to finish this lecture by focusing on this, which is something I didn't get a chance to tell you about earlier, and I want to get a chance to tell you now. Yes, faces of others are important to us, as is the ability to recognize ourselves. You saw me kind of struggling with this here. Whoa, it's even harder to tell upside down. Is that me? I'm like, is that me? Is that what I look like? You know, sometimes we like to know whether things are us or not. And I like to tell you about this weird process that somebody came up with. So first of all, I'll give you the whole story because it's kind of a fun story. There's a guy named Gordon Gallup. He's the senior investigator. He had a student working in his lab, and the story goes like this. The student was shaving in the mirror one day trying to figure out what to do for his PhD. What's my PhD going to be about? He worked in an animal lab, an animal research lab, and he had this thought while looking in the mirror that mirrors are kind of odd. Mirrors are not common in nature. I mean, the closest nature has to a mirror would be like a perfectly still body of water. But for the most part, most animals probably have never seen their reflection, or at least have never had the time to actually study their reflection in any detail. And so he thought, what happens if you expose animals to their own reflection? So he started hanging mirrors up in all of the animal cages. And what he found was that animals went through up to 3 steps, but not all of them hit step 3. Step 1, which every animal hit, was when they first saw the mirror reflection, they treated that reflection like it was another member of their own species. So if it was, you know, a bird and it suddenly sees its reflection in the mirror, however it would act to a new bird being introduced, that's how it reacts to the mirror reflection. Okay, so if it's the fighting territorial type, it might, you know, go after and try to attack that bird. Orcas, by the way, killer whales, very interestingly, will often bring a fish to a new killer whale. And so there's this cool recorded video online where the orca is trying to give the reflection a fish, a sort of gesture of friendship. But clearly the orca is still thinking of this as another entity. By the way, there's some really funny examples of primates when they first deal with, especially territorial ones, when they first deal with the reflection, of just being confused as heck because they're all about domination and subordination. And so at first the leader will get really aggressive and try to attack that mirror image. But of course, every time he gets aggressive and tries to attack, so does the reflection, because it's a reflection. And so as they come really close, then they back off. But as soon as this guy backs off and gets submissive, so does the other guy, which makes this guy want to be aggressive. But then so does the other guy. And so these poor little leader monkeys are like, what the hell? Every time I get aggressive, he gets aggressive. Every time I get... So at any rate, you get the idea. It's funny. All animals start there. Many animals hit step 2. What step 2 is they figure out at some point that I don't know what this reflection is, but it's not hurting me, and it's not helping me. In fact, it's It just is. It's there, but it has no consequence to me. And so eventually they learn to do something we're going to call habituation, but they learn to basically just ignore that thing. It's like it's not there. This is what most dogs reach, by the way. Dogs, usually if they first see themselves in a mirror, they might bark or do whatever like it's another dog. But if they've been exposed to a mirror for a long time, they just stop looking at it, and they stop being interested in it. And that's as far as most dogs get. That's as far as a lot of animals get. They just ignore their mirror reflection. However, certain animals take it a step further. And this is the really interesting step. Certain animals start looking at the mirror differently. They start paying attention to that reflection and kind of using the mirror as a tool. So chimpanzees were the first ones that we saw doing this. They would do things like the following thing. They would open their mouth. And they could look inside their mouth. Normally they can never see inside their mouth. They would also, I won't do this to you, but they would turn around and stick their butts in the mirror and look over their shoulder at their butt. They can never usually see their butt, so they get a chance to see their butt. Now, come on. I know, you've never done that. Sure. Okay, we'll pretend that's true. So they were using it to self-inspect. And Gordon Gallup and his student thought this was fascinating. Why is it fascinating? Because it suggests the animals have a sense of themselves. They recognize themselves in the mirror. Self-recognition, self-awareness. And so it was seen as a very powerful indication of that. In fact, they formalized a procedure which, when it's done on animals, it's called the mirror test. When it's done on children, it's called the rouge test. But it's really the same test. And the way it works is as follows. We would wait, so if it were animals, we would first expose an animal to a mirror and let it go through those 3 stages, okay, if it can go through the 3 stages. So we would just let it get used to the mirror, whatever that might be. Then at some point when it needed, say, dental surgery, or for some reason it had to be anesthetized, when it's under anesthesia, when it's out cold, we would put a mark on it. So this is showing a mark kind of under his cheekbone here. In the classic studies, they would put a mark on one earlobe and on one eyebrow. But the other earlobe and the other eyebrow would not have a mark. So imagine sort of some red lipstick, if you will, on an earlobe and on an eyebrow. Now, they made sure that this lipstick didn't smell like anything, no odor. They made sure it didn't produce any tactile stimulation, so it didn't feel itchy or anything weird. And so the idea would be that the animal, when it wakes up, has no idea that it has anything on it. And in fact, when you watch the animal wake up and recover, by the way, you remove the mirror or you cover it at first. And so the the animal is recovering, and sure enough, it's not touching its face or reacting to its face in any way. Once it's recovered, you remove the veil of the mirror or you reintroduce the mirror. And the question is, what does the animal do? And what you see with chimpanzees and with many primates, as kind of shown here, is that they look at the mirror image and they start touching the areas that are marked. And the nice thing about this procedure is you can compare, how often do they touch the areas with marks compared to the other similar areas that are not marked. And what you see is they touch the marks a lot. In fact, they do things like this. And it's basically like they're saying, what the heck is on my face? And that's powerful because it includes the word my face. It seems to suggest that the animals have a sense of self, a sense of self-recognition. When people say, how can you ever know what's in an animal's mind? Well, this is a process that tries to get at that. Can an animal recognize itself? It turns out that with variants of this task, elephants pass this test, dolphins pass this test, killer whales pass this test, a lot of primates pass this test, some birds pass variants of this test. So there are a whole lot of other animals that pass this test, which suggests they have self-awareness. And even the ones that don't pass, that doesn't mean they don't have self-awareness. So for example, for me, the heartbreak was the dogs. The dogs don't pass the test. I love dogs. Well, then when I thought about it a little bit, dogs aren't very visual animals. So what you'd really, dogs are all about smell. So what I would love to see somebody do with a dog is take its smell. You know, I'm a dog named Fred. Take the essence of Fred, whatever it is that I smell like to other dogs, and now put that somewhere where I haven't been. If you can put that somewhere where I haven't been, now how do I react to that when I smell that? Do I react to that like, oh, that's me, but I wasn't here? If that dog shows some sort of confusion or special interest in its own odor being somewhere it shouldn't be, then that suggests it recognizes that odor as its odor. Okay, so the point being here, you know, we're using visual experiments because we are visual beasts, but when you are trying to understand the mental world of animals, we can't necessarily just assume they're going to react to things the way we do. We may have to get into their world a little bit. But the bigger point is, this suggests a lot of animals are self-aware. And of course, this comes back to that point that I like to resonate through this course. So why do we do research to them that we wouldn't do to ourselves because it would be unethical? Well, if you think it's because we're self-aware and they're not, the evidence doesn't favor that. We're not sure if animals are self-aware and how their self-awareness might be different. By the way, this is also done with children. You don't anesthetize them, but you do. Typically, it'll be just a mother with some rouge on her thumb or something that'll just stroke the kid's head and then, you know, sneakily put a little mark on their head when they're not looking somewhere or something like that. And then a little later introduce them to mirrors. What we find with children is up till they're almost over 2 often, they don't seem to recognize that they have something on their face. Early on, and you're kind of seeing this here, children react to their mirror image like it's another child. And in some videos, you see them looking behind the mirror. So if you want to look for any of these, look up a rouge test. And you'll see they're often looking behind the mirror, looking for that other kid. And it takes them a while to recognize themselves in the mirror. One of the important developmental milestones. So we can use this to study how self-awareness develops in humans as well. And it is. So, all very cool. Again, it's always tricky in intro psych. You can only, tell a story about so much stuff. But in this perception story then, I focused on vision. But we've talked a little bit about the basic visual process that the eye uses. We've talked about how that comes together with memory to produce perception, what we perceive. And then in this lecture, we've talked a little bit about recognition, recognizing what we perceive. So what are things? Where are those things? And then we spent a little bit of time here specifically on faces and our faces in specific. So hopefully that gives you a sense of perception. You'll be doing your next M-Tuner Thursday, Friday this week, and then we'll be launching into Chapter 5 after that. Cool. Excellent. I'm going to leave it here. Thank you very much. Bye-bye.